Okay, so we're doing DC machine speed control of DC motors. This is relevant for N5 and N6 chapter 1. So speed control of DC motors. The first thing we are interested in is figuring out circuits. So for circuits, we have three main circuits. We have this one, the series circuit. I'm not going to sketch them the way you see them in your textbooks, but they're still series. So in a series circuit, we have your armature. It's connected in series with a field resistance. So we have our terminal voltage. The current which comes from the terminal voltage is expressed as the line current. The same current is the same current which will pass through our armature resistance, so we say it's IA. The same current which passes through the armature is the same current which will pass through the field current, so we have IF. So we are saying IL is the same as IA is the same as IF. Now, they may require you to find the total resistance of this whole circuit. It will be expressed as RAC. It's not so much of a requirement for you to find it, but we would express this as R total, but it says AC to say the armature circuit resistance, total armature current resistance. Armature circuit resistance. So in this case, these two resistors, RA is connected in series with RF, so thus you have RA plus RF. Additionally, you have the formula for back or generated EMF. So that EMF is just around here. To find that EMF, you're saying EMF equals to your terminal voltage minus your armature current times the total resistance which it will pass through. In this case, it's going to pass through RAC. Alternatively, you can write the same formula as V minus IA into the total resistance, which is RA plus RF. So you need to bear in mind for this specific circuit, RF refers to the series field resistance, just for this circuit here. Sharp. So next circuit, we have the shunt. So under shunt, we have your armature circuit. It's connected in parallel with the field resistance. Here's your RA, your terminal voltage, your IL. So IL, when it gets to this junction, it goes to the armature. Some current will also pass through the field. So on the shunt, your shunt current then is your terminal voltage divided by the resistance of the shunt field resistance, RF, where we have RF here. To find our armature current, we say IL minus IF. Because IL is IA plus IF, you get IA and IF, they'll all add back to IL down here. And then your formula for back EMF around there, the formula for generated EMF then says V minus IA RA. So this is your formula for the formulas which you need to make sure you know under shunt. Now comes this circuit. Now before we continue, we are still saying, by the way, in this shunt that your RF in this case is the shunt field resistance. Sure. So in the series field, series circuit, RF is series field. In the shunt circuit, shunt field. So these are the main two circuits which they'll give you. It's either they'll give you a series circuit or a shunt circuit. Then they'll modify your circuits. They might add a new resistance connected in series with these, a new resistance. They can decide to add a new resistor here or even there. So when they do that, then it will affect maybe how you find your field current or the total resistance passing through the armature circuit. So this one comes as a condition as part of the things they'll add. So what they'll do is they'll give you a series circuit and add a new resistance connected in parallel with one of the field resistors. So the scenario for this one, they give us the original circuit which we have at the top. We have your armature connected in series with the field. So in this scenario, you have your RA, this is RF. So I'm saying they add a new resistance connected in parallel with the field. This resistance typically it's referred to as the diverter resistance. So we still have our current IA. Here, when IA gets to this junction, some current will be diverted to the diverter resistance, some current will go through the field. So we only concentrate on the field current. Now for this specific circuit, when you're looking for your field, we use the current divider rule. When we use it, we say RD over RD plus RF times the armature current. So when you come across this circuit, at least you need to make sure you remember this equation. Additionally, for your total armature circuit resistance, your RAC, you have RA connected in series with this parallel connection. To express it, you have RA plus RD times RF over RD plus RF. This is our two resistors which are connected in parallel. Lastly, it's the formula for EMF. So EMF says V minus IA times the total armature circuit resistance. Alternatively, you're saying for E, V minus IA into the whole formula for RAC, which is RA plus your RD times RF over RD plus RF. So this is how you would have to go about these three circuits. So like I told you, this one comes as part of the conditions they've added onto the original circuit. So you are mainly interested in remembering your current divider rule equation. I trust you enough to know how to compile your formula for total resistance when they're connected in series parallel. Now comes the main part of this whole calculation. So the whole calculation revolves around EMF and torque. So the main formula for EMF and torque says EMF is proportional to speed and flux, and torque is proportional to armature current and flux. So when we compile the formulas, we then say E1 over E2 equals 2, N1 flux 1 over N2 flux 2. For torque, we have T1 over T2 equals 2, IA1 flux 1 over IA2 flux 2. So these are the two main equations which we need to make sure we know for EMF and torque. Now these two formulas have conditions, and the first conditions we want to discuss are flux conditions. So the first condition says this. It says if no info is given about flux. Therefore, flux 1 will be the same as flux 2. If you read a whole calculation, you collected your data and they did not say anything about useful flux, then you consider that flux is constant. Number 2, if you read the statement, assume that the flux is saturated. Same thing as the previous one. You'll say flux 1 is the same as flux 2. So no given information, flux 1 is the same as flux 2. Assume that the flux is saturated. Flux 1 is still the same as flux 2. So based on these first two conditions, here's how we apply them into the two formulas for EMF and torque. So we say, so if EMF is proportional to speed and flux, and torque is proportional to armature current and flux, but we are saying flux 1 is the same as flux 2. Therefore, in the formula for EMF, you do not need to substitute flux. And the reason why, even the formula for torque, you don't need to substitute flux, because if you're saying flux 1 is the same as flux 2, they cancel each other out. So eventually this section of the formula, you will not need it, even that one, only because those variables or values are the same. So we will not include it at all in our formula. So that's how it works. Then we have these ones. For the first one, it says assume the flux is proportional to the field. So according to this one, it says assume flux is proportional to the field. It's very explicit, it's very straightforward. In this case, flux will not be the same as flux 2, but not necessarily all cases. And you will see it later in your calculations. Number 4, it says assume the flux is unsaturated. When you read such a statement as this one, you'll continue to say flux is still proportional to the field, and that flux 1 is not the same as flux 2. Number 5, it will say assume a straight line magnetization curve. Same, flux proportional to the field, flux 1 not the same as flux 2. So based on these three, here's what you then do is, so you're saying if EMF is proportional to speed and flux, and torque is proportional to armature current and flux, but you're saying that flux is proportional to field current, the only thing you will do here is wherever you have flux into on the original formula, you will substitute your field current. That's all. So anywhere you have flux T1 over T2 IA1, where I'm supposed to have flux, instead of writing useful flux, I'm writing IF1 over IA2 IF2. And so that is how you would use these conditions. These are the main conditions they typically ask us about. I don't see them asking us anything else beyond these. So now, related to these conditions and circuits, let's go back to circuits. So circuits and let's say flux proportional to the field. So we started with the series circuit. On our series circuit, we had an armature connected in series with the field. Now, in this case, I'm going to come up with scenarios. My first scenario, they've given us the original circuit, which is the one I'm sketching now. Here you have your RA. So in here we have our RA, where we have IA, IF, RF. So we have IA1, IF1. So if there's anything we've learned about a series circuit is that IL1 is the same as IF1 is the same as IA1. So let's say they give us a new circuit which is still connected in series. So if there's anything new about this circuit is they've added a new resistance in series. So here's my new resistor. Oops, sorry. So I have my terminal voltage here. So for this circuit, I have IL2, I have IA2, this is RA, I have RF, which means I have IF2, and I have, let's say, R series, new resistance. I don't need to express the current for this one because it's the same as all other currents. So in this case, I have IL2 equals 2, IF2 is the same as IA2. I'm only going to be dealing with the formulas for EMF and flux being proportional to the field. So original circuit, this one, new circuit. So according to the original formula, it says EMF is proportional to speed and flux. Torque is proportional to armature current and flux, but they told us that flux is proportional to the field. So you say, therefore, E1 over E2 equals 2. We covered this now. N1 IF1, where I have my useful flux. Instead of writing useful flux, I'm writing field current all over N2 IF2. I have, for this side, we write in torque T1 over T2 equals 2 IA1 IF1 over IA2 IF2. These formulas can be expressed differently. So remember, under series, IF1 is also the same as IA1. Our IF2 is also the same as IA2. So maybe instead of writing field current in a series only, I decided to use armature current. Then your formulas would change to E1 over E2 equals 2 N1. Instead of writing field current, I'm writing armature current IA1 over N2 IA2. For torque, this is T1 over T2. Now for torque, I have IA1. I want to substitute another IA1. So IA1, like we are saying, the field current is the same as the armature current. So I'm saying IA1 times IA1, then I should get IA1 squared all over IA2 squared. And so this is your alternative representation for your EMF and torque equation. You can represent it like this. Next, going to the shunt. We're still discussing flux being proportional to the field. So for the shunt original circuit, there's my resistance. So the normal circuit for the shunt, all we had was this. Now with this one, it needs me to maybe use examples which have some values. So this is 1, this is RF terminal voltage. This is my original circuit. I'll create another circuit this side. I'll add a new resistance in series with my armature here. So here's my new resistance, but the whole circuit is still a shunt. The only difference is that I've added a new resistance. So this is RA, we can say this is RX, and then this is RF. So in this case I have IL2, I have IA2, I have IF2. So we only discussing flux being proportional to the field and the formulas for EMF. In such a case as this one, you've read the statement flux is proportional to the field. Now what's bound to happen? Let me create values like, let's say they give us a terminal voltage of 400 volts, field resistance of 200 ohms. Same as the new circuit, you'll still have terminal voltage 400 volts, field resistance 200 ohms. You have read the statement, assume that the flux is proportional to the field, and you want to write your formulas for EMF and torque. So in this case, already we know armature current won't be the same, but I'm not interested in that. I'm interested in flux being proportional to the field. Now for the shunt circuit, let's say you decided to find your IF1 and your IF2 for both circuits. The difference is they've added this new resistor here. So now for your IF1, you're still saying V over RF. In this case, you have 400 divided by 200, you'll get 2 amps. For your IF2, you will get V over RF, which is 400 over 200, which is 2 amps. You go to your formulas for EMF and torque. EMF proportional to speed and flux, torque proportional to armature current and flux, but they said flux is proportional to the field. Now here's what I'm trying to show you related to a shunt circuit. So E1 over E2 equals to N1 IF1 over N2 IF2. T1 over T2 equals to NA IA1 IF1 over IA2 IF2. Now the only thing which has happened is a new resistance was added in series to with the armature, but the field was not affected. The original field resistance, they did not add a new resistance. So thus, when you find your field current IF1, you will then notice it will also be the same as your IF2. So in a shunt circuit, they typically just add this resistance here. And because now your IF1 is the same as IF2, eventually in the formulas for EMF and torque, you don't need to write it. You can write it if you want. Alternatively, you can just express your formula as E1 over E2 equals to N1 over N2. Formula for torque, T1 over T2 equals to IA1 over IA2. So here's the last scenario of a shunt. In this case, they have not added a resistance in series with the armature, but they've added the resistance in series with the field. So in this one here, IL1, IA1, IF1. So I'm saying we've added a new resistance in series with the field. So it's still shunt, an armature. So here's my field and here's the new resistance. With this scenario, your IF1 will not be the same as your IF2. So in this case, when you look for your IF1 for this circuit, you're saying IF1 equals to the terminal voltage over the field resistance you have. In here, I still have Rx. So my IF2, this is 2, is going to be V over my total resistance here, which you just add these. So it's just going to be Rf plus Rx. So with this scenario, the principal EMF proportional to speed and flux, torque proportional to armature current and flux, but flux being proportional to the field, this formula then works out very well. You can easily substitute your IF1 and your IF2 because they are not the same. So even for torque, T1 over T2 equals to IA1 IF1 over IA2 IF2. So I hope it makes sense how to come up with these formulas. The additional conditions, last ones, and B. So they may tell you also assume the torque remains constant or the same. In this case, they're saying your T1 is still the same as T2. When you come across such a value, you may then say, therefore, T1 over T2 is equals to 1. The whole idea is I've made T2 the subject, T1 over T2 the subject, so I just divide both sides by T2 and I left 1 on the other side. So you can express it either like this or as they gave you in the question. The next one, it says the flux has reduced by 20%. In such a case as this one, we always assume the original value. If they're using percentage expressions, then we will assume the original value is at 100%, which in per units is the same as 1. So now if it's going to reduce, they'll say it has also decreased. So if anything is reducing or decreasing, we need to subtract the original. So you're going to say 100 minus 20 and you will get 80%, which during your calculation you can express it as 0,8 when you substitute into your formulas. Number 3, they can say the torque has increased by, let's say, 40%. the speaking percentage value. So you're still saying your T1, since we're speaking of torque, T1 is still going to be 100%. So if it's increasing, it's going to be 100 plus 40, which is going to be 140%. Which other conditions? We have number 4. The speed has been halved. If they're saying the speed is halved, it is the original speed which has been halved. So you're saying n2 equals to 1 over 2 times n1. If you're not writing it like this, you're saying n2 equals to 0.5 times n1. It's either you'll leave your expression in this manner. Alternatively, you want to make n2 the subject of the formula. So you divide both sides by n1. So you'll have n2. We say therefore n2 over n1 equals 2. You just take this n1 around there. So thus you have 1 over 2. So during your substitution, for n2 you're substituting 1. For n1 you're substituting 2. For the other side, if you're using this one, you're still dividing both sides by n1. So if that's the case, you're saying n2 over n1 equals to 0.5 divided by 1. With this one, this is n2 over n1. So with this method here, your n2 you're going to substitute 0.5, your n1 you're going to substitute 1. Next condition, number 5. The torque has developed by 60% of the full load, or the rated value. So in this case, when you read such a statement as this one, all you will do is you will say T2 equals 2. Now 60% of any value would be 60 divided by 100 off. So off, it means you're multiplying that value. So in this case, 60% of the rated value, or our full load values are primary values. So in this case, it would be T1. So you can express it as 0.6, which is 60 divided by 100 times T1. You can leave your expression in this manner. Alternatively, you can divide both sides by T1. So you say, therefore, T2 over T1 equals to 0.6 over 1. When you substitute your T2 equals to 0.6, your T1 equals to 1. And then what else? They can tell you something like, I did not want to add this one, but let's add it. The torque is pro. So they'll say that torque is proportional to the square of the speed. So the same torque is proportional to the square of the speed. This is meant to just show us the substitution into the formula for torque. So usually we say torque is proportional to armature current and flux. Typically in this specific case, flux 1 is the same as flux 2 during that calculation. You read the condition, torque is proportional to the square of the speed. So all they're saying is On the original formula, wherever I have torque, instead of writing torque, I substitute N1 squared over N2 squared equals to my armature current. Remember, flux 1 is the same as flux 2. If they happen to give you information for flux 1 and flux 2, then you will know what to do. But the condition revolves around here. So these are our equations and standards for speed control. And we will try to answer maybe 1 or 2 questions. Sure. Hello, Mary. So for this one, they've given us this following information. It says a 500 volt terminal voltage, 500 volts. It's a shunt motor. Here's our circuit. RA, RF. This is L1, IA1. Takes 90 amps from the supply. Our supply comes from the terminal voltage. So we are given IL1 as 90 amps. When running at 600 revolutions speed, 600 revolutions per minute. The armature resistance is 0, so RA is 0,1 ohms. The shunt field resistance R shunt is 250 ohms. It says calculate the speed at which the motor will run if the load torque is decreased by 20% and the resistance of 0,25 ohms is connected in series with the motor. So we are looking for N2. Calculate N2 if torque has decreased by 20%. So our T1 is 100%, which is 1. Our T2, 100 minus 20 is 80%, which is 0,8. Not only that, and the resistance of this amount, we have a new resistance. Our Rx is connected in series with the motor. The motor they're referring to is the armature. So there we have this new resistance here. This whole circuit is still a shunt circuit. So we have, this is our new circuit, RA, RF, RX, RF. So we have IL2, IA2, IF2. And it says, assume the flux is proportional to the field. Assume flux is proportional to the field. Now, yeah, this is our question. So they're telling us find N2. To find N2, the formula which allows us to find N2 is the one for EMF. So it says EMF is proportional to speed and flux. They told us flux is proportional to the field. Now let's check. Flux is proportional to the field. In this case, you can deal with a couple of things quickly. Already, you can see the circuit for field is not affected at all, even though we are going to need to find our field current, but technically your IF1, where you will say V over RF, will be the same as the one for the second circuit, V over RF, your IF2. So because IF1 is the same as IF2, we can add it here. IF1 is the same as IF2. Therefore, when we are looking for our speed, we don't need to substitute field current. So our formula is going to be this one. So since it's this very equation here, we need to find E1, E2, N1 is given, and we are looking for N2. So when you start with your calculation, to find E1, the circuit for E1 is this one, where we're going to say E1 equals to V minus IA1 times the resistance IA it's passing through. So we need to find IA1. It's a shunt circuit. So let's start. Our calculation actually starts from here. So they did not give us IA1. We're going to say IL1 minus RIF, our IF1. So to start, we start here. Our voltage, we have 500 over 250. We have 2 amps. We have 2 amps. We found our field current. And then now we can find IA1. We're saying IL1 minus IF1. So they gave us 90 minus 2. We're going to get 88 amps. From there we can find E1 by saying V minus IA1 RA. So our voltage, we have 500 minus 88 times our armature circuit resistance 0,1. You type your calculator, 500 minus 88 times 1. You'll get 491,2 volts. Now that you found your E1, you need to find E2. The circuit for E2 is this one here. So the formula for E2, let's remove this information or move it. So the circuit for E2 is this one on the right hand side. So it says E2 equals to V minus IA2 into the armature circuit resistance here. So for our armature circuit resistance, we have these two resistors. We don't have IA2. So to find our IA2, we'll use the formula for torque. So you'll say torque is proportional to armature current and flux. They told us flux is proportional to the field. We have discovered that IF1 is the same as IF2. We did this comparison here earlier on. So thus we'll just say T1 over T2 equals to IA1 over IA2. We are looking for IA2. You can make it the subject. You'll have your IA2 as T2 times IA1 over T1. So our T2 we got 0,8. Our IA1 we got 88. So it's going to be 88. Okay, this is divided by 1. So divided by 1, 88 times 0,8, 70,4. We have a 70,4 amps. From here, you want to go to the formula for EMF. So for your formula for EMF, E2. Before we find it, let's find the total resistance here. The resistance between there and there. So this is RAC. This is going to be RA plus RX. You can jump this step. So this is going to be 0,1 plus that RX value they gave us how much? 0,025 ohms. 0,025. We have 0,1 plus 0,025. We'll get 0,125 ohms. You look for your E2 using V minus IA2 RAC, where we have 500 minus our IA2, we got 70,4 times 0,125. 500 minus 70,4 times 0,125, and we are getting this number which we have never seen before in our lives. So just because you're getting the same value as E1 doesn't mean you always get the same value for E1. So now that you found your E2, you're looking for N2. We'll make N2 the subject. So it's going to be, you cross multiply, it's going to be what? E2 times N1 over E1, and we have 491,2 times our N1, they gave us 600 over 491,2. Our answer is 600 revolutions per minute. So where our steps, we started here, we found our IA2, we found our our IF1, we found our IA1, then we found our E2. From here, we looked for the current connected, the armature current, by using the formula for torque. After we find our IA2, we found our RAC, and last step we found N2. So chances are this calculation might be out of 6 marks. We have 7 steps, but it can be 6 marks. Yeah, so go practice.